NCERT Class 9 Science. Chapter 1. Exploration. Entering the world of secondary science. 1 mark questions answer in 1 word or 1 sentence. Question 1. What does the magnifying glass framing the page numbers of the textbook symbolize? Answer. It symbolizes careful observation, noticing patterns and paying attention to what might otherwise be missed. Question 2. What does the compass framing the page numbers of the textbook remind us about? Answer. It reminds us that exploration needs direction, choosing appropriate models, asking the right questions, and knowing the limits of where our ideas apply. Question 3. What are scientific models? Answer. Scientific models are simplified ways of looking at real systems that focus only on what is most important for a given question. Question 4. How is a presented model? Moving car in a physics. Answer. A moving car is represented as a single point. Question 5. How are atoms and molecules represented in chemistry models? Answer. Atoms and molecules are drawn as spheres and bonds. Question 6. How is the Earth treated as a model in Earth science? Answer. The Earth is treated as a smooth sphere layered into distinct regions. Question 7. What does the symbol c represent in science? Answer. C represents the speed of light. Question 8. From which Latin word does the symbol c speed of light originate, and what does it mean? Answer. It comes from the Latin word celeritias, meaning speed. Question 9. What is the exact defined value of the speed I of light today? Answer. 299,792,458 meters per second. Question 10. What is a law in science? Answer. A law describes a regular pattern observed in nature, often expressed using words mathematical relationships. Question 11. What is a theory in science? Answer. A theory provides an explanation of any certain patterns occur, based on evidence gathered over time. Question 12. What are principles in science? Answer. Principles are broad ideas that help us make sense in a given situation. Question 13. Name the Indian featured in the Physicist Meet a Scientist section of Chapter 1. Answer. Meghnad Saha. Question 14. What was the total fuel requirement, in kilogram, of the aircraft in the miscalculation incident? Answer. 22,300 kilogram. Question 15. By how many liters was the aircraft short of fuel in the mid-flight incident? Answer. About 15,000 liters. Question 16. Approximately how many liters of air does a person breathe in one day? As per example 1.3. Answer. About 10,000 liters. Question 17. How many breaths does a person take per minute at rest? Answer. About 12 to 15 breaths per minute. Question 1. What is the volume of breath? Answer. About 0.5 liter. Approximate air 1N1. Question 19. How many minutes are the estimation in example 1.3? There in a day, as used in? Answer. 1,440 minutes, 60 times 24 equals 1,440. 2 to 3 marks questions, answer approximately in 30 words. Question 20. Why does building scientific model involve making assumptions and deliberately ignoring certain details? Answer. The natural world is complex and studying it in full detail is often impossible. Scientific models deliberately ignore irrelevant details to keep things simple enough, yet still allow us to find answers to what we are looking for. These are purposeful choices, not mistakes. Question 21. In example 1. The cricket shot. What details would you keep and what would you ignore in a simple model to predict weather boundary? Answer. Keep mass of the ball, speed and direction in which it has been hit. Ignore in a simple model brand of the bat, color of the ball, amount of grass on the field, air resistance, spin of the ball and stitching of the threads at the seam. As the model becomes more complex, these ignored details can be added for greater accuracy. Question 22. Why must scientific language be very specific and precise? Answer. Scientific ideas must be communicated clearly and unambiguously. To allow scientists across the world to describe observations, compare results and build ideas together, science uses a shared language of specific terms, symbols and units. Everyday words like force, work, cell and reaction have very precise, specific meanings in science that are different from their common usage. Question 23. What role does mathematics play in science, according Chapter 1? Answer. Mathematics is a language that helps scientists think more clearly about the world. An equation is not just a calculation tool, it is a compact statement about how certain things are related. Using mathematics in science means understanding the situation first, identifying relevant quantities and then using mathematical relationships to reason carefully, not just to find numerical answers. Question 24. What is the difference between a scientific law, a theory and a principle? Give one example of each. Answer. Law describes a regular pattern in nature using words or mathematical relationships. Example. Newton's laws of motion. Theory explains why those patterns occur, based on evidence gathered over time. Example. Atomic theory explains how molecules are formed. Principle. A broad idea that helps make sense of a given situation. Example. Principle of conservation of energy applied while climbing stairs. Question 25. What approach Meghnad Saha used to study stars and what did this simplification allow him to discover? Answer. Meghnad Saha did not try to model every atom, every reaction, or every movement inside a star. Instead, he treated the matter in a star as a hot gas. Ignored many complex processes and focused only on temperature, pressure, and how atoms formed ions. This simplification allowed him to explain how the color of a star is deeply connected to its surface temperature. Question 26. Why are standard SI units important in science and daily life? Answer. Standard SI units ensure that measurements mean the same thing everywhere, allowing scientific results to be compared and ensuring fairness in trade and daily life. The airplane fuel incident in the chapter shows the danger of unit mix-ups. The aircraft ended up about 15,000 liters short because pounds per liter were used instead of kilograms per liter. Using SI units everywhere avoids such conversions and errors. Question 27. What helpful strategy does Chapter 1 suggest for solving in science problems tackling situations? Answer. Chapter 1 suggests 1. First understand the situation being studied. 2. Then identify the quantities that matter. 3. Finally, make a rough estimate to check whether an answer makes sense. Exact values are not always necessary, especially in the early stages of reasoning. An approximate estimate is often enough to tell whether a result is reasonable or impossible. 5 marks. Question answer descriptive more than 60 words. Question 28. Explain the concept of scientific models with examples from 4 different branches of science. Why is deliberate ignoring of the of considered a strength and not a mistake? Answer. The natural world is complex, and studying it in full detail is often impossible. To make sense of this complexity, science uses models, simplified ways of looking at real systems that focus only on what is most important for a given question. Examples of models from different branches of science. 1. Physics. A moving car may be represented as a single point. All its complex parts, shape, and structure are ignored because they are irrelevant when studying its motion. 2. Chemistry. Atoms and molecules are drawn as spheres and bonds. This ignores the internal structure of atoms but helps in understanding how substances combine and react. 3. Biology. Cells are shown as diagrams highlighting key parts. When studying how the heart pumps blood, many individual cells are ignored so that the organ can be understood as a functioning system. 4. Earth science. The Earth is treated as a smooth sphere layered into distinct regions. This simplification is useful when studying large-scale planetary behavior. Why ignoring details is a strength. Building a model involves making assumptions and deliberately ignoring certain details. For example, when studying the motion of a falling object, air resistance may be neglected. To understand the basic effect of gravity. These choices are not mistakes, they are done on purpose to keep things simple enough, yet still allow us to find answers to what we are looking for. As models are developed further, more details can be added for greater accuracy. Therefore, simplification in models is a purposeful tool of science, not a flaw. Question 29. Describe Meghnad Saha's contribution as mentioned in the chapter. What does his approach teach as simplification in science? Answer. About Meghnad Saha. Meghnad Saha was an Indian physicist who studied the light emitted by stars. His work is featured in Chapter 1 as a powerful example of how scientific simplification leads to significant discoveries. His approach. Science often begins by ignoring details. When Meghnad Saha studied light from stars, he did not try to model every atom, every reaction or every movement inside a star. Instead, he treated the matter in the star as a hot gas. He ignored many complex processes. He focused only on temperature, pressure and how atoms formed ions. His discovery. This simplification allowed him to explain how the color of a star is deeply connected to its temperature. Stars that appear blue are hotter, stars that appear red are cooler. What his approach teaches us. 1. Simplification is not a shortcut, it is a deliberate and powerful scientific tool. 2. By reducing a complex system to its most essential features, scientists can uncover relationships that would otherwise be hidden. 3. As confidence in the model grows, more details can be added step by step. 4. Science does not require complete information to begin, it requires the wisdom to know what to focus on. Question 30. What is the between a law, a theory and a principle in science? Explain each with an example. Is a scientific theory just a guess? Give reasons. Answer. In the secondary stage of science, students come across 3 important types of scientific ideas: laws, theories and principles. Each has a specific meaning. 1. Law. A law describes a regular pattern observed in nature. It is often expressed using words or mathematical relationships. Example. Newton's laws of motion, they explain the jerk felt when a bus stops suddenly. 2. Theory. A theory goes a step further and provides an explanation of why those patterns occur. It is usually based on evidence gathered and tested over time. Example. The atomic theory explains how molecules are formed. 3. Principle. Principles are broad ideas that help us make sense in a given situation. Example. The principle of conservation of energy, applied, for instance, when climbing upstairs. Is a scientific theory just a guess? No, a scientific theory is not a guess or an untested idea. It is an explanation based on careful testing and critical examination. Always open to improvement and revision when new evidence becomes available. Subject to change if new evidence demands it, but only based on evidence, never on opinion or belief. This openness to being corrected is a key feature of science that makes it reliable. No scientific theory is ever final, and none is beyond question, and that is precisely its greatest strength. Question 31. Explain the role of mathematics in science as described in Chapter 1. How is an equation more than just a calculation tool? Answer. Chapter 1 explains that as students explore science more deeply, they will notice that it uses language in a very careful and precise way. Mathematics is one of the most important parts of this language. Mathematics is a language, not a hurdle. Mathematics in science is not meant to be a hurdle or obstacle. It is a language that helps us think more clearly about the world. Learning to use mathematics in science does not mean memorizing equations. It means 1. Understanding the situation first. 2. Identifying the relevant quantities. 3. Using mathematical relationships to reason carefully. An equation is more than a calculation tool. An equation is a compact statement about how certain things are related. Example. Describing motion using quantities like distance, time, and velocity allows us to answer questions about where an object will be at a later moment. Similarly, mathematical expressions are used to describe 1. Rates of chemical reactions. 2. Patterns of population growth. 3. Changes in energy within a system. Mathematics is a tool for thinking. Mathematics becomes a powerful language for thinking, not just for finding numerical answers. If a student focuses on understanding the situation and the quantities involved, will begin to feel less like obstacles and more like helpful guides in their exploration of science. Q.32. What is meant by scientific predictions? How do predictions help drive further exploration, even when they fail? Use examples from Chapter 1. Answer. Chapter 1 describes the predictions as one of the ability to make most remarkable strengths of science. What are scientific predictions? When laws, theories and models are well established, they allow us to anticipate what will happen under new or different conditions. These predictions can be made before performing an experiment, and in many cases even when an experiment cannot be performed at all. Predictions are not guesses, they are reasoned expectations based on evidence and careful thinking. Examples from the chapter. When predictions succeed. When predictions match observations, confidence in the underlying science grows. When predictions fail, scientists do not reject ideas based on opinion or belief, only on evidence. When predictions do not match observations, scientists re-examine their assumptions, models, or measurements. Even the most successful scientific theories have limits and may fail when new conditions are explored or when measurements become more precise. Such failures are not a weakness of science, they are its greatest strength. No scientific theory is ever final and none is beyond question. Conclusion. Prediction is a powerful tool that drives further exploration and a deeper understanding of the world, regardless of whether the prediction succeeds or fails. We can predict ideas about motion, how far a kicked football will travel. Knowledge of chemical reactions, how much carbon dioxide will be produced, how soft a baked bread will be. Biological principles, how one's breathing will change while running. Question 33. Using example 1.3 from the chapter, process of explain the scientific estimation. Why does the values careful reasoning perhaps much more than accurate calculations? Answer. Chapter 1 introduces students to the important scientific skill of estimation. Making reasonable approximate calculations to check whether an answer makes sense. Example 1.3 Estimating liters of air breathed in one day. Step 1. Estimate number of breaths per minute. At rest, a person takes about 12 to 15 breaths per minute. Approximate value used. About 15 breaths per minute. Step 2. Calculate total breaths per day. There are 60 times 24 equals 1,440 minutes in a day. Total breaths approximately 18,000 22,000, roughly 20,000 breaths per day. Step 3. Estimate volume of one breath. It takes about 4 to 5 breaths to fill a typical rubber party balloon. When inflated, a balloon holds about 2 liters. Therefore, one breath is 0.5 liter. Step 4. Calculate total volume. 20,000 breaths by 0.5 liter equals 10,000 liters per day. Cross-checking with balloon example. A person could fill about 3 balloons per minute. 3x 2 liters by 1,440 minutes equals 8,640 liters, reasonably close to 10,000 liters. Confirming our estimate. Why science values careful reasoning over accurate calculations. Exact values are not always necessary, especially in the early stages of reasoning. An approximate estimate is enough to tell us whether a result is reasonable or impossible. Learning to estimate helps build intuition, detect errors, and develop confidence in thinking. The aim is not to find the exact number, but to check whether the answer makes sense. As the chapter states, science values careful reasoning perhaps much more than accurate calculations. Question 34. Describe the airplane fuel miscalculation incident mentioned in Chapter 1. What lesson does it teach about the use of standard units in science? Answer. Chapter 1 presents a real incident to illustrate why standard units matter in science and everyday life. The incident: a passenger aircraft ran out of fuel mid-flight due to a mix-up in units. The flight needed 22,300 kilograms of fuel in total. However, the ground crew used the wrong unit. They calculated the fuel using pounds lb per liter as the density, instead of kilograms kilogram per liter. As a result, the aircraft was loaded with far less fuel than required. The aircraft was about 15,000 liters short of fuel. Luckily, the aircraft could glide to an emergency landing. The aircraft was damaged, but there were no casualties. Why this happened? Pounds and kilograms are very different units of mass. Using the wrong unit led to a serious miscalculation that could have been fatal. Lessons from the incident. 1. Standard SI units are critical. They ensure that measurements mean the same thing to everyone, everywhere. 2. Unit mix-ups can have serious real-world consequences, not just in science, but in aviation, medicine, engineering, and daily trade. 3. Using SI units everywhere avoids conversions and errors. 4. This also connects to everyday life. When we buy a kilogram of rice or vegetables, we expect it to mean the same amount everywhere, based on agreed international standards, not local objects or opinions. Question 35. What does Chapter 1 tell us about science as a human activity? How does it grow and develop over time? Answer. Chapter 1 closes with an important reminder about the true nature of science, that it is far more than facts, equations, or experiments. Science is a human activity. Science is a human activity shaped by 1. Curiosity, asking questions about the world. 2. Creativity, imagining new explanations and models. 3. Collaboration, working with others, sharing results. 4. Careful questioning, testing ideas rigorously before accepting them. How science grows. Science grows as people. 1. Ask questions. 2. Test ideas. 3. Share results. 4. Learn from mistakes. Science develops over time through the work of many individuals across different cultures and generations. It is not the product of a single person or country. The self-correcting nature of science. No scientific theory is ever final and none is beyond question. When predictions do not match observations, scientists re-examine assumptions, models, and measurements. This openness to being corrected by nature itself is what has allowed science to help us understand the world. Why scientific thinking matters beyond the classroom. Even if a student does not choose to study science beyond grade 10, scientific thinking will be very important in whatever they do. It helps 1. Understand the technology that surrounds. 2. Evaluate information critically. 3. Make sense of the world we live in. Science invites students not only to learn about the world, but also to learn how we are trying to understand it. Question 36. How does Chapter 1 use the example of a solar eclipse to teach scientific thinking? What does it say about checking viral claims on social media? Answer. Chapter 1 includes a Threads of Curiosity box that applies scientific reasoning to a commonly circulated belief about solar eclipses. The viral claim, food should not be eaten during an eclipse because it becomes harmful. This claim circulates widely on social media. The scientific approach, asking simple questions. Rather than accepting or rejecting the claim based on belief, Chapter L shows how to disprove it. Using simple scientific question. 1. What physical change occurs during an eclipse? An eclipse is simply a play of shadows. The moon comes between the earth and the sun, blocking sunlight temporarily. 2. Does temperature change significantly during an eclipse? No significant change in temperature occurs. 3. Does food go bad if it is left in a shadow? No, shadows do not cause any chemical or biological change in food. Conclusion. No physical, chemical or biological mechanism supports the claim that food becomes harmful during an eclipse. Disproof comes simply from asking logical scientific questions. Broader lesson. This example teaches students that scientific thinking is useful far beyond the classroom. It equips us to critically evaluate information we encounter in daily life, including on social media. Rather than accepting claims based on tradition or opinion, we should ask, what evidence supports this? What measurable, testable mechanism would explain it? Question 37. What is the difference between a law, a theory and a principle in Science in Exploration Chapter 1? Answer. According to Chapter L, a law describes a regular pattern observed in nature, often as a mathematical relationship, e.g., Newton's laws of motion. A theory explains why those patterns occur, based on evidence gathered over time, e.g., atomic theory. A principle is a broad guiding idea applicable to a situation, e.g., conservation of energy. Importantly, a scientific theory is not a guess, it is a rigorously tested explanation. Question 38. Who is Meghnad Saha and why is he mentioned in Class 9 Exploration Chapter 1? Answer. Meghnad Saha was an Indian physicist who studied the light emitted by stars. He is highlighted in Chapter 1 as an example of how simplification is a valid scientific tool. Instead of modeling every atom and reaction inside a star, he treated stellar matter as a hot gas, ignored complex processes and focused on temperature, pressure and ionization. This helped him explain why the color of a star is directly linked to its surface temperature. Question 39. Why are SI units important? What happens without standard units? Answer. Chapter 1 discusses a real-world incident where a passenger aircraft ran out of fuel mid-flight because the ground crew used pounds per liter instead of kilograms per liter, leaving the plane about 15,000 liters short. The plane made an emergency landing but was damaged. This example shows why globally agreed SI units are critical. They prevent conversion errors and ensure that scientific results can be fairly compared worldwide. Question 40. What is a scientific model? Can you give an example from Chapter 1? Answer. A scientific model is a simplified representation of a real system that focuses only on what is most relevant to a particular question. Chapter 1 gives several examples. In physics, a moving car can be modeled as a single point. In biology, cells are shown as diagrams. In earth science, the earth is treated as a smooth layered sphere. When modeling a cricket shot, the brand of the bat and the color of the ball are ignored, while the mass of the ball and its speed and direction are kept.
तो उम्मीद है कि आज की ये जानकारी आपको पसंद आई होगी। अगर आपके मन में कोई भी सवाल है तो कमेंट्स में जरूर पूछें। सुषमा एक्सप्लेन से जुड़ने के लिए और ऐसे ही इजी लैंग्वेज में मुश्किल चीजों को समझने के लिए चैनल को सब्सक्राइब करना ना भूलें। मिलते हैं अगले वीडियो में, तब तक के लिए अपना ख्याल रखें।